75% of the knowledge you believe could be wrong because pseudoscience says so. Well, that's a bit of a mixed bag there. I am curious as to how you get the number 75%, but let's say that for sure a good chunk of what you believe could be wrong and likely is wrong, not because of what pseudoscience says. Pseudoscience is trying to get to a conclusion, determining the conclusion first, and then trying to find your way to it. So, he who debunks the tin foil. Where'd you come up with that name? That is a great name.
I do a lot of like pseudoscience debating.
Oh, nice.
So like flat Earth, crystal healers, hollow earthers, the moon is plasma, the world is energy, frequency, vibrations, literally every pseudoscience thing.
Yeah, you're doing the Lord's work, by the way.
And by the Lord, you mean Carl Sagan, or?
Yeah, I'm just saying that's the thing that people like. Personally, like I would not last 5 seconds with like a bunch of flat earthers, but I'm glad there are people who can take it. So
like I've been on, you know how like some panels you can have like 8 people on there? I've been on panels where I have like 8 flat earthers and it's just me.
Wow. I really, really wonder how far this flat earth thing is going to go. I mean, I don't know if there's more people, or are we just like seeing them because of social media now? And they've always been there in these numbers. Is it expanding?
I feel like it's generational.
There's definitely more.
Wow.
There's definitely more. Like if you compare like when the movement started in like 2016 to like now, like it's grown radically.
Started,
and that's really sad.
Do you know how it started?
No, but that's when it got really popular, like on social media, I believe.
Yeah.
It goes to like the 60s and maybe even earlier. Like we've known Earth was a globe since like Plato or like Pythagoras.
That's true. That's true. Yeah.
I'm an agnostic, by the way. So your question, is the Bible the evidence or the claim of a God? I think that would be the claim of that specific God, and there would need to be other stuff to prove. Like that is not the evidence from my point of view. But I did want to ask you, I think for me personally, I think the most like intuitive argument for a God is like ones that like are sort of fit like the first cause sort of arguments. Like cause and effect is such like it's such like an accepted universal thing for people at this point. So it's like when one thinks of like the chain of cause and effect that like goes on into the past, it comes to the point where it's like, is that causation and effect endless, or is there a first cause at some point, like something that sets off like the dominoes essentially? I just wanted to get sort of your take on that.
I have a little concern that perhaps cause, as we think of it and know it, may not be a thing outside our universe. I'm not convinced that we have to carry that concept across the border of before, quote unquote, our universe, because we literally know almost nothing about what's over there. So I mean, because once you get outside the universe, you lose the laws of physics, and cause may be one of those things that we lose. As intuitive as it is, it's really hard to get away from that.
Yeah, I kind of take the exact same position that like the cosmology, or like the studying of like deep space and time, like the origins of our universe, like it is still like just from stuff I'm not like a cosmologist, I'm not even like an amateur cosmologist, but just from like lectures I've watched, that like it seems like it's a possibility that like cause and effect starts at like a certain time, but like there are still things existing before that, in whatever sense the word before means, like before like there's time, which is why this is such like a mind scrambling sort of concept for me to talk about.
It is. And the other problem I have with it is if you say quote unquote God's out of time and space, then there's no temporal ability there. If there's no time, nothing can change. So therefore, he can't create. All he could do, or it, or whatever the force is, doesn't even have to be a sentient being, is exist. So I don't see that outside of time and space, it's a good assumption to say that something outside could then create. So that seems to be another flaw.
Yeah, I would sort of agree with you. Yeah, but like I said, it's only because like that argument is just so intuitive, because in our lives, like we all sort of like recognize like the sort of legitimacy of cause and effect.
Yeah.
That like there's nothing really that happens in like any human's experience that happens without a cause. It's possible that that's based off like a lack of understanding of like deeper time and space and those sorts of things.
Yeah, and what it does is it takes away it, even though we don't understand it. The concept itself works as a hypothesis, and then that takes away the deductive arguments, right? Because in the tag argument, because in a deductive argument, if your premises are true and one follows the other, then your conclusion must be true. So that they literally do. They make it as a deductive argument, not realizing that they're squishing in some assertions and assumptions in there. And when you put those things in there, we don't know that the cause isn't a thing, but we also don't know that it is. And if it could go either way, then it is no longer a deductive statement. It's no longer an absolute statement like 1 + 1 = 2. You know.
Yeah, see, that's funny, because like 200 years ago, I probably, like, just based off that argument, I probably would be a theist, like, pre-deep space cosmology. But it's just like there are like things still to be like physically discovered that might contest these sort of like intuitive arguments that like we've traditionally made for like existence of like a first cause or a first mover or something like that.
Yeah, it really is just a recognition of our ignorance at that point. Don't take your assumptions to the point of belief, to the level of belief, when there are still low-level assumptions. So
yeah, I think we can like sort of like build on sort of like very like I wouldn't blame anybody like prior to like the modern age for like sort of building off like a sort of like a sort of cause and effect view, because like they were literally hundreds of years, like at least hundreds of years away from before they would even be able to think about having the sort of technology which might allow them to start questioning those sorts of assumptions.
Yeah, and now that we are post the quantum era, right, the discovery of quantum mechanics, we know there are things that happen without cause, right? You know,
or seemingly so,
or at least seemingly so, yeah. Which at the very least, that's a 50-50 then. The creation of virtual particles, and you know, when does a radioactive atom decay? What triggers that decay at that moment? So it's either we don't know, or it's either it does it without a trigger, because it's just a potential thing that can happen at a random time. So cause actually may not be a thing even within our universe. So
exactly.
It may not be an absolute thing, let me put it that way.
Yeah, which is, you know, even today is still mind-breaking for me. So
totally. Me too. Graham, you had something?
Yeah, if I ask you guys the question, if we rewound time, would it replay out exactly the same?
I don't know, because I mean, if the universe is completely deterministic, you could kind of say probably would, but then again we have that quantum mechanic problem, because if things happen, and frankly everything may have a random quantum mechanic source to initiation, you know, what initiates a thought or something like that, then it wouldn't, right? Because it would all the probabilities of of how things would change from 1 second to the next would be based on probabilities and not just deterministic causes. And since we don't know that, which way it goes, we don't know I don't know which way to be confident of.
Yeah, I would answer in a similar, like, intuitively, it feels like it would happen the same way, but it really depends, I guess, on, do any of, like, these sort of seemingly random, like, particles and, like, the way they act, like, if we were to replay the universe, like, could one of these particles have done a different thing in that moment and that would have led to something different? Like, I literally don't know.
Yeah, I mean, you know, I forget who said, if it was the Heritage or Graham, that, you know, when something decays, right, it's going to throw off an alpha particle, a wave or a photon of something, and that's going to interact with something else. But when, at that moment that it decays, was that a cause thing that we're not actually aware of the cause, or was it just completely a random thing? And if it's random, you're talking about, like, you know, Marvel Universe type multiverses. So
Yeah, that would be my response too. We're too ignorant on the microscopic scale to make such a claim.
Yeah.
And what I know about quantum mechanics is it's inherently tied to probability, and you're contingent on the fact that all the probability would happen like as it would, which is so probabilistically low that it's hard to make a claim that's yes or no. I would be on the fence of maybe, like, is it possible? Like, sure, but, like, is it likely? I doubt it, because there's always going to be some interaction that we can't fully know to its extent that could have done something else, and it could fundamentally change, like anything, like X thing.
Yeah, it's like a couple shows ago we were talking about the Penrose hypothesis about the universe, how it could expand to highest entropy, or is it lowest entropy? I think it's lowest. I gotta figure that out. Anyways, and then it would be identical to a Big Bang, pre-Big Bang singularity, and it could burst again because the conditions would be the same. And the question came up is like, well, does that mean that our universe would repeat historically and each of us would exist again and that sort of thing? And who knows? I remember reading a book by Frank Tipler, who was a physicist, about 20 years ago before he passed away. And that was kind of his theory or his hypothesis or belief even, that we'd all come back eventually, but it would be like 100 trillion years down the road. So don't bother giving it that much thought. So,
I mean, when, like, there's certain notions about the Big Bang that are definitely misconstrued, like the existence of singularities. Like, for me, like, what I tell people is they don't exist. They're just a mathematical garb. Yeah. It's just showing you that this quantum, like this classical theory we have, is breaking down. And unfortunately, general relativity is very classical, and there's no quantum theory of it like that of quantum electrodynamics or like electroweak theory, for example. So the idea is that you have this thing, and when it leads to infinities, you have something that went wrong. It's been historically shown too, like if you look at Maxwell's electromagnetism, when a positive charge and a negative charge get too close together, so the attractive force goes to infinity, and so does the kinetic energy of the system. Mm-hmm. And once we developed a more quantum theory of electromagnetism, the infinity went away, which is another type of singularity. And that's kind of the whole push for quantum gravity. It's like, well, every time this thing happened, when we got a quantum theory, it went away. So that's really the big push. And we know our universe is fundamentally quantum. We just know that.
Yeah. What strikes me is suspicious though about a singularity is that I got to reformat this. Sorry, it's off to the left of this. But look at that quark quark epoch, about 2 inches down. Experimental evidence starts right at that time. Right, this is where the first four forces start to decouple, and we start to see the just after the earliest quarks as 10 to the minus 12ths of a second. So that is not too far away from time zero. So even though the time before that is hypothetical, and then you're going all the way back to time zero, which may or may not
infinitely
exist.
away from time zero.
Say again?
Or it's infinitely far away from time zero.
Well, I
would propose that there are no zeros in an infinite set.
Yes, I understand, but I mean, there's also infinites within infinites, right? But there's an infinite number of numbers between any two numbers too. So there's nested in infinites. But I mean, the point I was trying to make though is like if you go from, just give me for the sake of the sentence at least, that if a time zero exists, at least hypothetically, there's not a lot of time between here and here, and we know that this happened for sure. So this is where our ignorance is, and this is something we haven't not been able to generate enough energy with current particle accelerators to prove. This is still mathematical, I believe.
Yeah.
So
I still hate Congress for not giving Texas that super collider.
when was that? It's like 10 years ago or something when they budget that.
And now it's like a water facility, I think. They spent
plenty of water coming in there.
They spent like $4 billion like digging out the whole area, and Congress was just, or people in power were like, no, we can't use it for propaganda.
Was that going to be bigger than CERN? I assume that would be the purpose of it.
I believe so. I think it was, if not bigger, like probably close to the same size.
Yeah.
It was like it was canceled in 93, I think.
Wow.
And like now the project is gone, and that makes me really sad, because I think it would have done more with supersymmetric theories, which.
What do you know about that? I don't understand supersymmetry. Do you know it well enough to explain it?
Yeah, I know like a general amount to explain it, but like I don't know all like the ins and outs of like Brian Greene's theories.
Can you give us a little bit of it, or?
Yeah, so I guess the more general idea is that every particle has like a super partner, which has different properties. So it's like saying each particle in nature, like electrons or quarks, have sort of a twin, and these twins have some differences, and specifically their spin, which is like a property of particles. So in the standard model, particles fall into two categories based on spin. They're like fermions, like electrons, or bosons, like photons. And fermions make up matter, while bosons carry forces. So supersymmetry suggests that each fermion has a boson superpartner, and each boson has a fermion superpartner. So the core idea is that supersymmetry could solve and explain why the mass of particles doesn't blow up to infinity when you try to include like quantum effects. It could also explain dark matter, which is a really big problem, or not problem, but it's something that everybody.
It's unanswered.
Yeah, it's one of the forbidden fruits of questions.
Yeah.
There's the push for it is something called the hierarchy problem. It's so like in physics, like the Higgs gives particles, like fundamental particles, their mass, but the mass of the Higgs itself should be incredibly large due to quantum effects, so large that it's hard to explain why it isn't as heavy as the fundamental forces of nature would predict. So supersymmetry offers a solution by canceling out some of these quantum corrections, which keeps the Higgs mass at a reasonable-ish level. it balances the equations in a way that the Higgs doesn't become unreasonably heavy, which unreasonably is just ambiguous, or so I've been reading so far.
So when you say superparticles, are you meaning largely massive?
So
Super in that sense, or what?
are you talking about when I say super partners?
Super, yeah. Are they,
Yeah,
does
so
that mean they're massive? What's
yeah,
larger
so
than their partners?
so they're more of so the way that I would describe it is they have their spin is mostly what I'm talking about. So each particle, they have they have pairing with their super partner, right? So whose spin differs by half a unit. So if the original particle is a fermion, its super partner is a boson, and vice versa. So supersymmetry predicts I think 6 or more particles to exist, so the electron, so the fermion, this spin 1.5, and there's something called the selectron. It's the bosonic superpartner of the electron.
So these are in addition to the standard model particles.
Yeah,
and we haven't found any of them yet. Right?
No.
Yeah,
That's kind of the push for the LHC.
yeah.
Well, we haven't found any of them. It could be that they're at some energy scale, and we just don't have the technology to probe those high energy physics.
Yeah, that seems to be our current limitation. We've filled out the standard model, but don't seem to be able to go further.
Unfortunately, it's so common for that. We have so many mathematical things that are sound, but we're limited by our resources, and it's sad.
Yeah. Well, I remember, Syrian, and I think it was getting down to here, going from this barrier down to this barrier, if you will, that to develop a super collider to determine this experimentally would take something on the scale of either the circumference of the Earth or something like that. And then there was another one that was just like the orbit of the Earth. So I don't know if that's this one and then this one. So this may not ever be practical. So I don't know. It's fascinating stuff. How do you know this about supersymmetry? Did you study it? Have you read about it, or?
Yeah. So I've been reading about it. I wanted to do dark matter stuff, so that's kind of that's one of the big things you start at first.
Yeah.
But the problem is with dark matter is all the theories, or not all of them, but most of them that we have, they have no experimental evidence that suggests that they're even correct.
Yeah.
So it's really demotivating when you look at X theory and you read about it and you realize dude, there's no proof of this. What am I wasting my time on? But at the same time, there's always the universe doesn't have to conform to what it should be. It just does what it does.
Well, and this is a frontier, and this is what we do in a frontier. We sometimes have to do a certain amount of guessing. We try to base it on something, right? In physics, it's usually math, but sometimes, and people like Penrose will do this, and even Lawrence Krauss has admitted to doing this. Just make it purely philosophical. What if this, and then try to find a way to not rationalize it, but find supporting math or something like that, and then hopefully you can figure out a way to test it, or at least figure out what it would take to test it. So go ahead.
Ironically, supersymmetry was introduced to solve a fine-tuning problem, which was the Higgs, so I was talking about. It isn't much heavier due to quantum corrections, but supersymmetry itself requires fine-tuning. So if the superpartners are too heavy, then supersymmetry doesn't fully protect the Higgs mass from growing too large. So you were it's not circular, but it's hard to really fully know this, because it seems counterintuitive, but it's also a little contradictory, just a little bit.
So, do you have a book you can recommend to us? that you like?
For supersymmetry, no, not really. But there's some really good like PDF books that you can find by general physicists that push supersymmetry. There was one by Brian Greene, I think.
Yeah.
And
Okay.
it's fairly layman. The problem is when you get to like these dark matter theories, the math just becomes unreasonable.
Yeah. He's pretty readable. The problem with Brian Greene, he's got the he's a proponent mostly of string theory, as I understand, and
Yeah.
he's really put his whole career into that almost. So he's a little biased toward that, and it still has the problem of not being testable currently. But someone's got to do it, right? And someone will break through at some point, hopefully, with one of these hypotheses.
Yeah, though Brian Greene is he supports like both sides of the coin. Like he goes for symmetry, then there's super symmetry or string theory, my fault, and then he goes for super symmetry. He doesn't really, from what I've seen recently, like he's still promoting both. Like he doesn't have like one side. I think though that he's pushing like a version of string theory that involves supersymmetry.
I gotta say, it is frustrating because they've been stuck for quite some time now, right? We got so far through quantum theory and well, it was only 2012, 2014 when they finally discovered or experimentally determined the Higgs particle.
Yeah, the big problem is that the smarter we get, the harder it is to progress. Like if you go back to Newton, you're like, well, shit, dude, like this is all common fucking sense. Well, at the time, no, it wasn't.
Yeah.
And when you take the leap to relativity, it's like a 250-year like difference, and you realize, well, okay, so this isn't as intuitive, but it still kind of makes some sort of sense. And then when you make the jump from relativity to quantum mechanics, you're like, okay, well, wait a minute, like how are we getting all this? And then when you make the jump now, you're like, whoa, we've discovered most of what our technology is capable of doing. Now, most of what we predict is far beyond what we could ever build right now, and it's a big problem to keep it up.
Well, it does give us the lay people some time to catch up. I will say that. I mean, it seems like there's like 100-year lag, 50 to 100-year lag for the science, the new science to get to the public, and this is a really hard one because it's unintuitive, right? It's hard to understand. So I recommend to everybody go look at the PBS Space Time series, which is now probably hundreds of videos long. There's some other good people too that I like, but because we all want to understand this stuff, or at least better than we do, and it takes time. Gosh, it takes time. It takes time to. I still don't consider that I get relativity, even though I think I understand it, but it's weird.
Yeah, general relativity, like at first, when you first learn it, it's kind of intuitive, but when you try to fully submerge yourself in all the math and the ideas in it, it's very unintuitive. Like I was explaining on another live that under general relativity, you don't have energy conservation. And so energy can be created and destroyed because energy isn't conserved in general relativity. And it's kind of hard to explain that because it's mostly math.
Yeah. So what's your background?
I do physics.
Professionally?
Not yet.
Not yet? You're working on a degree or something?
Yep.
Very cool. Very cool. Do you do live, sir?
No, I don't have enough followers. I think I have enough followers, just that like I just don't want to do it because like the people I follow, I also follow flat earthers. Because like when I go live, I want to jump in there. So like I can't imagine like if I had like a dark matter live or something where I'm like, well, this is what I'm trying to do, and a flat earther just requested and was just being very obnoxious in the comments and barking.
Well, I mean, there are people who debunk flat earthers on here. I know there's just saying physicists are popular. They always get a good audience. So it's and I'm all for as many science communicators as we could possibly have. So
Yeah, I love science. I love science communicating, especially with concepts of general relativity and quantum mechanics, because like even though most people don't understand it, the implications of both are fascinating, and they contradict a lot of what you're normally taught in like high school or like
yeah,
your first couple years in like classical mechanics.
yeah.